Have you ever wondered not just who you are, but where and when you are? We exist within space and move through time, but what are these things really? Are they solid realities or constructs of our minds? From ancient stargazers to modern physicists, humanity has tried to grasp the invisible architecture of the universe. Our journey will peel back the layers of here and now, exploring whether space can bend, time can slow, or if time itself is an illusion. This is more than a history lesson. It's an investigation into the operating system of the cosmos and our place within it. The questions may be more important than the answers. Our story begins in ancient civilizations, long before the advent of modern science. We journey back to a time when humanity first gazed at the stars and began to ponder the very nature of existence. These early cultures, scattered across the globe, laid the foundation for our understanding of space and time, grappling with concepts that continue to challenge us today, where time was not just a measure, but a tool for survival and order. The rising and setting of the sun, the changing of the seasons, these were the rhythms that dictated life, shaping agricultural practices, religious ceremonies, and social structures. Time was intimately connected to the natural world, a force to be understood and harnessed. Egyptians saw time as a resource, a river that could be navigated, a cycle that could be predicted. Their elaborate calendar system, essential for agriculture and religious observances, reflected a deep understanding of celestial movements and their impact on earthly affairs. The pyramids themselves stand as testaments to their mastery of engineering and their profound connection to the cosmos. Indian thinkers imagined vast cycles of creation and destruction, cosmic epics spanning unimaginable lengths of time. Their philosophies explored the cyclical nature of existence, the eternal dance of birth, life, death, and rebirth. Time was not linear, but a grand, repeating pattern, a concept that resonates with certain aspects of modern cosmological theories. In Greece, Plato, the renowned philosopher, called space a container, a receptacle for all things. He envisioned space as an infinite and unchanging void, providing the stage upon which the drama of existence unfolds. And time, the moving image of eternity, a fleeting reflection of the eternal realm of forms. Time, in Plato's view, was imperfect and transient, a shadow of the perfect and unchanging reality that lay beyond our senses. While Aristotle, Plato's student, saw space as the relationship between objects, a network of connections defining the position of everything in the universe. And time as the measure of change. For Aristotle, time was inextricably linked to motion and transformation. It was the yardstick by which we gauge the unfolding of events, the continuous process of becoming. Without movement, without change, there would be no time. Time, therefore, was not an independent entity, but a property of the physical world, a consequence of its inherent dynamism. These early debates set the stage, the foundation for centuries of philosophical and scientific inquiry into the fundamental nature of space and time. Is space a background, an empty stage upon which the universe plays out, or just the relationships between things? Is it a fundamental aspect of reality, or simply a convenient way to describe the relative positions of objects? Even the Inca, high in the Andes, unified space and time into one concept, Pacha, a holistic worldview that intertwined the physical world with the flow of events. This profound understanding of the interconnectedness of space and time, in a way, anticipating modern physics. Their sophisticated astronomical observations and intricate calendar systems demonstrate a deep appreciation for the rhythms of the cosmos. Across cultures, from the Fertile Crescent to the far reaches of Asia, the first thinkers gave us the language to ask, the tools to probe the mysteries of the universe. What are space and time, really? What is their true nature? Are they fundamental aspects of reality, or simply constructs of our minds? Their ideas, though formulated millennia ago, still echo in today's science, informing our understanding of the universe at its most fundamental level. The debate between space and time as independent realities, absolute and unchanging, or mere relations, dependent on the presence of objects and events, began here, in the minds of these early thinkers. And it's a debate that continues to this day, driving cutting-edge research in physics and cosmology, pushing the boundaries of our knowledge about the universe and our place within it. For centuries, philosophers argued whether space and time were real or just relations. Immanuel Kant changed everything by asking, how do we experience the world at all? He argued that space and time are not properties of the world, but structures of our minds. Like glasses we can never remove. We don't discover space and time, we impose them on our experiences. This means we can never know the world in itself, only as it appears to us. Space and time are real for us, but not features of ultimate reality. Kant's insight placed the origin of space and time within us, making them part of what it means to be conscious. The debate shifted from the cosmos to the mind. Before Kant stepped onto the philosophical stage, a monumental debate raged, a clash of titans that would echo through the halls of science and philosophy for centuries to come. Newton and Leibniz, two of the greatest minds in history, found themselves locked in a profound disagreement over the very nature of space and time. Their perspectives, seemingly irreconcilable, offered radically different visions of the universe. Newton, with his groundbreaking laws of motion and universal gravitation, saw space as an infinite, boundless expanse, a stage upon which the drama of the cosmos unfolded. He envisioned it as an unchanging stage, absolute and independent of the objects within it. Space, in Newton's view, existed regardless of whether there was anything in it. It was a fundamental, unyielding framework. His famous bucket argument claimed water's motion proved space existed even if nothing else did. The curved surface of the water in the spinning bucket, he argued, demonstrated the reality of absolute space and its influence on motion. Time, for Newton, was a universal clock, ticking everywhere at the same rate, an absolute and uniform flow, independent of any observer or event. It was a cosmic metronome, setting the pace for the entire universe. Leibniz disagreed. Space was just the web of relations between objects, a relational framework defined by the distances and arrangements of things, not a container. He saw space and time as emergent properties, arising from the relationships between objects and events, rather than as pre-existing independent entities. He argued that absolute space violated reason. If the universe shifted 3 feet, nothing would change, because all the relationships between objects would remain the same, so absolute space was meaningless. It was an unnecessary and ultimately incoherent concept, adding nothing to our understanding of the world. For Leibniz, without objects, there is no space. Space, in his view, was not a void waiting to be filled, but rather a consequence of the existence of things and their interactions. Their debate defined science for centuries. Is space a stage, a pre-existing arena in which the universe plays out its drama, or a network of relations? A complex and dynamic web woven from the interactions of all things. Newton's view enabled classical physics, providing a framework for understanding motion and gravity that would dominate scientific thought for centuries. But Leibniz's ideas would return, finding new relevance in the development of relativity and quantum mechanics. The question, is reality built on absolutes, fixed and unchanging, or on relationships dynamic and ever-shifting? The answer would shape the future of science, influencing our understanding of the universe and our place within it. For centuries, Isaac Newton's vision of absolute space and time reigned supreme in the world of science. His laws of motion and universal gravitation were built upon the idea that space was a fixed, unchanging arena, and time flowed uniformly for everyone, everywhere. This framework provided a solid foundation for understanding the cosmos, from the motion of planets to the swing of a pendulum. But in the early 20th century, a new paradigm emerged, spearheaded by Albert Einstein, that would shatter these long-held beliefs. Einstein's special theory of relativity, a groundbreaking work, revealed that space and time are not absolute and independent entities, but rather are relative, intertwined aspects of a single entity. They are not universal constants experienced identically by all observers, regardless of their motion or location. One of the key postulates of special relativity is that the speed of light in a vacuum is constant for all observers, irrespective of the motion of the light source. This seemingly simple statement has profound consequences. To reconcile the constancy of the speed of light with the principle of relativity, time itself must slow down, and distances must shrink for objects moving at high speeds relative to an observer. The faster you move through space, the slower you move through time, and vice versa. This effect, known as time dilation, is not just a theoretical curiosity. It has been experimentally verified and is crucial for the functioning of technologies like GPS satellites. The implication is staggering. There is no single universal clock ticking away in the background of the universe. time is personal, relative to each observer's state of motion. But Einstein didn't stop there. His general theory of relativity, published a decade later, took these ideas even further, revolutionizing our understanding of gravity itself. General relativity posits that space-time is not merely a passive, inert stage upon which events unfold. Instead, it is a dynamic, flexible fabric, a four-dimensional continuum that can be warped, stretched, and curved. This fabric is warped by the presence of mass and energy. The more mass or energy concentrated in a region of space-time, the greater the curvature. And what we perceive as gravity is simply the curvature of space-time itself. Objects move along the curves and contours created by this curvature, following the path of least resistance through the warped geometry. Gravity is not a force pulling objects together, but rather a manifestation of the geometry of space-time. Space-time and matter are inextricably intertwined, each influencing the other in a cosmic dance. The distribution of matter and energy in the universe dictates the overall structure and evolution of space-time, shaping the cosmos on the grandest scales. Furthermore, space-time is not static. It can ripple and undulate, propagating gravitational waves, disturbances in the curvature of space-time caused by accelerating massive objects. These waves can travel vast distances across the universe, even through seemingly empty space, carrying information about the cataclysmic events that created them. Einstein's theories transcended the age-old Newton-Leibniz debate about the nature of space and time. Space and time are revealed to be neither absolute, fixed entities, nor simply relative relations between objects. Instead, they are dynamic, interdependent, and often behave in ways that defy our everyday intuition. They are strange, yet fundamental. Einstein's revolution irrevocably changed our understanding of reality itself, forcing us to abandon classical notions of space and time. The cosmos is no longer a rigid, static structure, but a flexible, evolving tapestry woven from the threads of space and time. The old certainties, the comfortable assumptions of Newtonian physics, were swept away, replaced by a universe far stranger and more wondrous than anyone had ever imagined. Time feels like it flows forward. Eggs break, people age, memories point to the past. Yet most laws of physics work the same backward or forward. Why does time have a direction? The second law of thermodynamics says entropy, disorder, always increases, making the arrow of time a journey from order to chaos. The universe began in a low-entropy state. Its history is a slide into disorder. Some link time's arrow to causation. Causes precede effects, but this can be circular. A few quantum processes do prefer one direction, but they're too weak to explain our everyday experience. Is time's flow fundamental, or just a byproduct of initial conditions? The source of the river of time remains hidden. The mystery endures. Einstein's relativity erased the idea of a universal now. Simultaneity is relative. What's present for you may be past or future for someone else. This leads to the block universe. All moments, past, present, future, exist equally in a four-dimensional space-time. The flow of time is an illusion. Our consciousness moves through a fixed landscape. This is the B theory of time. In contrast, presentism says only the present is real, the past is gone, the future unwritten. But relativity challenges presentism, whose now is real. The block universe, though strange, fits better with modern physics. Our intuition of time's passage may be just that, an intuition. The debate between these views is far from settled. We feel like the same person over time, but what does it mean to persist? Endurantism says objects are wholly present at every moment. They endure. Perdurantism, fitting the block universe, says objects are four-dimensional worms stretched through time. We are just one time slice of a larger whole. This view explains change. A statue has a new part at one time, a weathered part at another. Endurantism matches our intuition. Perdurantism fits modern physics. The debate reveals that persistence is a deep mystery. Are we enduring beings or collections of temporal parts? Even identity through time is stranger than it seems. Our journey has spanned ancient philosophy to the frontiers of physics. We've seen space and time reimagined, debated, and even questioned as illusions. Today, physicists find that at the smallest scales, space and time may not be fundamental at all. They could be emergent, like the wetness of water from H2O molecules. Some theories suggest space and time are projections from a deeper, timeless reality. The search for a theory of everything is also a search for the true nature of space and time. The quest continues, connecting us to our ancestors and descendants. As long as we ask where and when we are, the story goes on.